Let's do it. Good afternoon, everybody. Welcome to Algebra 2. So today we're talking about a new lesson. It's kind of new. Some of it's new. A lot of it's a review of Algebra 1. And if I had to say, one person asked me, what's Algebra 1 about? I'd say lines. Line, like y equals mx plus b, and point slope form, and slope, and all that kind of stuff. So it's a review of that. And there's a few other things I'm going to tack on to that are new, of course. This is a new course, so you're not going to have just a review all the time. That's not going to happen. Okay, warm up real quick. Write a rule for each function, then state the domain and range. Oh, I didn't do that last hour. I'm not going to do that. Forget the domain and range. Let's not do that. Write a rule for each function. Now, this looks really weird. This is a set. Okay, it just contains things, right? What things does it contain? That's a coordinate, isn't it? That's a coordinate. That's a coordinate. They're giving you points to plot if you wanted to plot things. But I think we can see what the relationship is between x's and y's, between any of these pairs, without plotting anything. Guys, in this thing, how are x and y related? Here's x and here's y. Here's x and here's y. Here's x. What's the difference between them?
They're all real numbers.
Yeah, they're all real numbers. What's that?
So y is just negative x.
Y, let's translate that, because that's our rule right there. Y is negative x. There's our answer. That's it. Every single one of them. You take x and make it negative. The negative value of x is what y is, and that's all you got to do on that one. Well, we'll get to that one in a second. Hold on, let's show this.
The negative 7 and 7.
Well, let's see. Is y negative x? What's x? X is negative 7. What's negative 7? It's back to positive 7. So it actually works out. We're cool. But thanks for checking all the points. I like that. Number 2, you guys see a pattern in the x's and the y's for each pair of these? Y is x times 3. Everybody agree with that? I agree. So y is, and you don't usually write x times 3, you usually write 3x. Yeah, equivalent kind of thing, but more user-friendly there. Done. Number 3. Anybody see any patterns in this one? Okay, 2y is equal to x, I'm hearing, which is fine. 2y equals x. But usually you don't want 2y. You just want y equals. How could you get rid of this times 2 really fast? You can divide both sides by 2. So an even better rule is y is x divided by 2. And it is. If you take any x coordinate and divide it by 2, you get the y coordinate out. Yay. Oh, it's exciting talking about something I've known for 30 years 3 times a day. Number 4. Anybody see that? X minus 1. So if you're saying if you take all the x's and you subtract 1, you get the y's. Everybody agree with that? If you take the x's, subtract 1, you get the y's. Okay. So if you take the x's and you subtract 1, it equals the y's. And we're all done. That's it. That was all your warm-up was. Pretty sweet, huh? Yeah, LG's. Long. Sorry. Many skills to talk about. Topic today is linear equations. I'm going to generalize that a little bit to other things that we'll study in the future, but a large chunk of this is linear equations. What's linear mean? The meaning's buried in the word. It's a line. Yep. So you see linear, we're talking lines, straight lines. It's nonlinear. It's not a line. It's something else. It's a curvy thing or some kind of other graph that we're going to have. So what those are and the differences between them and the review of the formulas you had for lines from Algebra 1. Also going to talk about intercepts and symmetries. It will take a while. Each of these sections is really comprehensive. I usually don't lecture like this much, but there's so much information in this new textbook. I guess I have to work harder. I know. Sorry.
I've always thought math teachers should have last hour plan.
Math teachers have double salary. That's what I think. I work twice as hard. I don't mean as a shot at anybody else, but my gosh, questions all day. The anger I get for simply teaching math.
Yeah, the anger towards you,
Yeah.
not just
The threatening voicemails.
Have you gotten them?
No.
Okay.
No, but
I wouldn't be surprised.
I wouldn't be surprised either. I wouldn't either. And when it doesn't make perfect sense, who's your anger come out on? Me. It's a delightful life.
Is it really though?
Don't get me started.
So what you're saying is become that.
You do whatever makes you happy.
No.
So not a math teacher.
You know, whatever job you have, you're going to have stresses and hassles. So
So you chose.
pick your poison. At least here I get out of here at 3 o'clock and I got my summers off. So it's a pretty sweet deal. I don't have to learn anything. I just sit here and say things I've known for decades just over and over again. It's pretty easy. All right, notes. Here we go. First things first, your first homework assignment online is due by the end of the day today, so hopefully you got that taken care of. There's a new one out there, homework 1.2. It's not due till Wednesday. You got 5 days for it. That's pretty sweet. So even if you're doing something interesting this weekend, you still have time to either watch the video, but you're not doing that because you're live, and work on the homework that's there. So that's pretty cool.
Are we going to get the entire lecture done today?
Yeah. 1 section a day. Speaking of, Tuesday will be a work day. You guys will be gone, so just work from home. And when you come back the next day, we'll probably just have a new lesson, and then work day, lesson, work day, etc., etc., etc. Okay, here we go. This is section 1.2. Section 1.2. I would at least title this as section 1.2. You know, if you don't want to write down the whole name of it, that's fine, but at least you know what we're talking about today. And if you can always go back to the online textbook later and do that. It's found on page 13 of your online textbook. 3 main topics I need to get over today: linearity, intercepts, and symmetry. Symmetry is by definition beauty. Yeah, exactly. I try to only date women that are like lopsided though, because I like asymmetry kind of stuff. That's just me. I got a lot of weird kinks you don't even want to know. Not in a sick way, just in a, why's it gotta be? Exactly. I'm just saying weird things. You guys are making it dirty. All right, here we go. Box. Write down the box. Trying to take their paragraph stuff and break it down for you. Nothing in this box should be brand new, but if I know my students, I bet we've forgotten them. Yeah. Shocker. Something's linear, like I've said before, if it's a line. There's 2 ways to see if something's linear. Number 1, you can graph it and look at it. If it's a line, hey, it's linear. Or if you're just staring at an equation and you're too lazy to go graph it, if every variable in the equation is only going to have x's and y's, right? If every one of them is just raised to the first power only, and you don't usually write x to the first, you just write x, right? You don't write y to the first, you just write y. So if you just see x and y, no x squareds, no y cubes, no x to the pi power, just x and just y, then you know it's going to also be linear. Creatively, if it's not linear, they call it nonlinear. I know. Geniuses winning. So if you graph anything and it has any curve to it whatsoever, it's nonlinear. If you look at equations and the variables have any powers in them that aren't 1, it's not linear. There are 3 main ways to represent a line, the equation for a line. First one's called the standard form of a linear equation. That one, ax plus, and a and b and c just stand for numbers. It could be 7 or 2 or whatever like that. That one doesn't come up too much. We won't harp on that. I probably won't even have that one on the test. But someday, if you're doing systems of equations or something with matrices or something like that, that might be a useful format, and we'll talk about that when we cross that bridge. By far, the two that you should know, though, are the bottom two. I'm sure you recognize those words. Slope-intercept form and point-slope. Yep. Those are your babies. Dang. Already? Oh. That's all right. Children don't need love.
Well, I guess that's what my mom thought.
It's okay.
Oh,
Yeah, just leave them in the crib. You gotta sleep, man.
Right?
They'll figure it out. It's just survival of the fittest.
I'm still alive. I had brothers.
And you turned out so well.
I had brothers and sisters.
Oops.
I got left in the kitchen. I had the greatest advantage. I was left in the kitchen. I had the greatest advantage of all.
If you look at the last two equations, their names, slope, intercept, and point slope, come from the fact that the slope is in their equations. Those are not equations for slope. A lot of times, and this happens all the time, a math teacher will say, guys, what's slope? And they'll say, oh, y equals mx plus b. That's not slope. Slope is rise over run. Yeah. This just tells you how quickly a graph goes up and down. It's not the equation for the graph. The equations for the graph are those two down at the bottom. If you like formulas, y2 minus y1 or x2 minus x1, okay stuff. We'll just practice all these skills at once. I'm going to start throwing some examples at you. A graph. Let's say at this point is up here at the coordinate 1, 6. And you have some point over here at, say, negative 3, 0. And these are 2 points on a line that's supposed to be straight. I'll leave that one be. Something like this. So if you're going to write the equation of a line, either one of these two, they got the word slope in them. You got to start by finding the slope. Okay, so it's rise over run. There's two ways you can go about this. You can look at the picture and see how much it rises by. Always go left to right like a book, okay? And how much it runs by. Let's go that route. Rise. What's the y value at this point? And it rises up to a y value of? So the rise was 6. Cool. What's the run? Well, that's about horizontal stuff, right? If I'm running, I'm going horizontally. So the x here is negative 3, right? This one's over here at 1. How far is it from negative 3 to 1? 4. Yeah, so that's 4. And please reduce things. So that would be 3 halves. Alternatively, if you want to use this formula because you don't want to think, and that happens sometimes, these stand for the points, right? x1 and y1 stands for one of the points. x2, y2 stands for the other point. So let's pick this point for the second one. The y value is 6, right? Minus the y value of the first one, which is 0, over this one, which is the x's, which is 1, right? Minus negative 3. What's 1 minus negative 3? Is 4. You get the exact same result, and you're okay. All right? So you got to be able to find slope. Are we okay on finding slope? Okay. Now, what can you do with it? You're supposed to use it to come up with an equation for this line. I bet everybody loves slope-intercept form the most, probably. That's the one you know, right? Y equals mx plus b. Yeah, it's pretty common. What's the b stand for? The intercept? Which intercept? The x, the y? The y, which is right here. Do you know where that is? No, not exactly. So can you use that form? No, actually the one that's probably more versatile is the one below it, the one called point slope. All you need to know is some point. This is a point, right? But you don't know it, but you do know this point, right? You know this point. You can use any of those points and the slope to figure out the equation. So let's go do point slope form. I'm going to use zeros. Yeah. Here's your equation for it. I hope we know what the m stands for. slope, right? What's the x0 and the y0 thing stand for? The coordinate of the, what's it called? Point. Okay, so you have 2 points, don't you? Pick one. Doesn't matter which one you use. Which one do you want? A, B, A, B, A, B, B. Done. Okay, this is the point I'm going to use. I'm just going to plug in everything I know, okay? You don't do the y and the x. You always leave them alone. But this y with the 0 stands for the y coordinate of the point you're using, which is 6, right? So this side is going to be y minus 6. Over on the other side, you got m, which we already found was 3/2, right? And then you got x minus, and the x with a 0 stands for the x coordinate of the point, which was 1. So here's my equation for this line. It works. It counts. It has an x and a y. What powers are the x's and the y's raised to? Which means it's what kind of equation? What's the 2 words? Linear. Yes, exactly. Good. Everybody's got that copied down by now, right? Okay, so people at home can see what we've been doing. We found the slope of this thing. You can look at it and review. We use point slope form. We plugged in the coordinate x0 and y0, 1, 6. That was on our graph. And we plugged in our slope as well, correct? I bet you are not used to writing that, though. You usually probably like the other one. What's the other one called? Not point slope, but slope intercept. You can turn this into slope intercept. What's slope intercept look like? It's just y by itself, right? Mx plus b. There is a way to make this thing look like that. First thing I would do is probably distribute this end. Remember how to distribute things? Okay, yep. So the 3/2 is times x, which is 3/2 x, right? 3/2 times -1 is negative 3/2. Why is this not looking like that yet? There's that 6 there, so what should I do with it? Let's add to both sides, yep. So y is 3/2 x minus 3/2 plus 6. Doesn't quite look like it yet, though. There's just supposed to be one number on the end, right? But I got 2. So guess what? You do have to do fractions. They never leave, no matter how old you get. So how do you add fractions? You need a common denominator. This is 6/1, correct? So to get a 2, I have to multiply the top and bottom by 2. So it's really 12/2, which is the same as 6, right? And then how do you add fractions? Just add the tops, right? Don't change the bottoms. So in the end, we have 3/2 x. If you add the tops, -3 plus 12 is +9, right? And you don't change the bottoms, do you? No, so plus 9/2. If you look at this, by the way, you don't have to write this down, but 9/2 is 4.5. And what's the number on the end represent? The intercept, correct? Oh, now do you know where it intercepts? Yeah, now I know that this is right here at 4.5. So you can figure out the intercept if you need to by just distributing things out and moving crap around. Okay. I don't want to belabor the point, but that's kind of all that's going to come up. Okay. You can find the slope, and you got any point on the graph, then you can plug in the point slope form, correct? And you can get it from there. I know it's a lot, but does it make sense conceptually? And if it doesn't, please let me know. Anybody? It's okay? Sure? Okay. That's it for, yeah. I'm posting this one. Yeah, I'm doing literally what I'm doing right now. I'm posting like after we're done. And you can always go back and review, right? That's good. I'll put the PDF out there. I'll do the whole dang thing. Yeah, of course. Here's another example. Not a graphical one. I'm just going to give you an equation, and I want you to tell me if it's linear or not, okay? Y is 3x plus 22. Linear or not? And how could you tell? And how do you know it's linear? These things are just raised to the first power. Yeah, done. Okay, we're good. How about this one? Y over 5 equals 6x plus 2 divided by 7. Looks scary. Still linear. Why? This is still raised to the first, and this is still raised to the first. Does the other crap matter? Nope. This is linear. How about that? Linear? No, not even close. That's nonsense. So that's what I'm trying to drive at here. You can look at a graph. You can see if it's a line, right? Duh. Or you can look at an equation and see if it's a line. Either way, you should be able to detect whether it's linear or nonlinear. If it is linear, you can find the slope. You can come up with an equation for it. If you know the y-intercept, you can just go right to slope-intercept form, right? But if you don't, you'll still know a point. You can plug it in and figure out the rest from there. All right, I've belabored that first topic enough. Here, let's talk about intercepts now. Intercepts. Topic 2 of 3 today. What is an intercept? That's such a good definition. I'm so impressed. You're a genius. Hey, at least you had the intelligence to read the board. Sometimes you just get blank stares. I'm like, it's right there. You could just read. Well, I don't think half of our kids can't read, though. I'm pretty sure half of you can't read. Like A, B, or C. Just a theory. I'm not sure it's based in reality. Yup. Even though they're math terms, you should always stop and say, do they make sense in the English context? If there's an interception in football, what happens? The football kind of intersects the player, something like that. It's intercepted. Well, same thing here. An intercept is just where a graph intersects or crosses an axis. That's it. There's two axes. There's the x-axis and the y-axis, so there's two kinds of intercepts. X-intercept, where it crosses the x-axis, and y-intercept, where it crosses the y-axis. You want to find an x-intercept, the thing that guides you is that y is 0 there. And if you want to find a y-intercept, the thing that should guide you is x is 0. Why? Well, we'll throw a graph up on the board in a second and see why. I'm just messing with you. Okay. You can whisper. I can't sass students when I'm recording. I was sassing some pre-calc kids the other day, and I said something mean to them, so I couldn't upload it. Like, whoops, I just ruined my whole work. Strawberry knows what I'm talking about. This topic of intercepts goes far beyond just lines. So I'm going to tell you a general way to look at this instead of just linear, but anything, linear, nonlinear, any kind of function we ever study all year long. The process will be the same to think about intercepts. No matter what weird graph you ever see, like this, there's an intercept. Can you tell me where the y-intercept is? That means where it crosses the y-axis. There's only one spot, right? Negative something, correct? Now, you don't know how far down it is. Do you know where this point is left and right?
0.
Yes. X is 0 at that point, correct? That's why the rule to find a y-intercept is to let x be 0. Makes sense when you think about it. What about all these other points? What about the x-intercepts? There's lots of those, right? Here, across the x-axis, crosses the x-axis, crosses the x-axis, crosses them. But for all of them, there's something you know about those points. You don't know where they are on the x-axis, but where are they up and down?
0.
Y is 0 there, correct? So that's what guides you for the x-intercepts. You don't know what the x is, but you know y is 0. That's why those rules are what they are, and it makes sense when you think about the graph. And if you're stuck on a test, Remember what we've talked about. Don't go figure it out for yourself for a second. You don't have to memorize a bunch of formulas. That's not what this class is about, but understand it. All right, well, let's try to find some intercepts. Y equals 3x plus 6. You can just spot the intercept, can't you? From old stuff. This is like y equals mx plus b, correct? What's the y-intercept, guys? Yeah, it is, right. You can just spot it, and that's what you were taught to do, right? But why is it the end number? Because wherever it crosses the y-axis, x is 0. And if you plug 0 in here, what's 3 times 0? And 0 plus 6 is 6. So this one would have a y-intercept of 6. That's it. That's y is the last number. How about this one? Y is 17x minus 36 all over 6. Is it linear?
Yes.
Mm-hmm. Where's the y-intercept? What you have to go off is x is 0. So plug 0 in. 17 times 0 is 0. 0 minus 36 is negative 36, which divided by 6 is negative 6. So whatever this line is, I don't know. I'm going to make up something. But it crosses down here at negative 6. Makes sense, right? And this is what kind of intercept? This is the y-intercept, correct? Okay. Let's do this one again. But this time, let's find the, not y-intercept, x-intercept. What do you know about an x-intercept? Y is 0. So I go back to my equation, and guess what I plug in for y? 0, exactly. Really got to go back and forth. So we're looking for an x-intercept on this one, so y is 0. You don't know what x is, but could you solve for it, guys? You can divide both sides by 3 if you want to right now. You could minus 6 first. Either one's okay. I would recommend probably the minus 6 first. But if you want to divide everything by 3, that's okay too. Because what do you have to do in this step? Divide by 3. So if you divide both sides by 3, negative 6 divided by 3 is negative 2. So I guess the x-intercept is negative 2. This graph, we can actually complete the whole thing now. Where was the y-intercept? You said it was 6, correct? The y-intercept was just 6, right? Yeah, so 1, 2, 3, 4, 5, 6. There's a point on my graph. The x-intercept is negative 2, correct? So this graph would look something like that right there. Makes sense, right? Nice thing about this is it's more general than this. It's not just about lines. This logic holds for anything. Try this one out. Example. Y equals x squared plus 3x plus 2. Ooh, that ain't linear, is it? That's going to be like some kind of U shape eventually that we'll get to. Nonetheless, the logic is going to be the same. How do you find a y-intercept for any funky thing? X is 0. Plug in 0 for x. That's 0 then, right? This is 0, right? So it's 2. So my y-intercept is just 2. You can either write the number, or this is a point where x is 0, right? Or you can write as a point. You could write or 0, comma 2. Either one's okay. I prefer the point, but I don't care. How do you find the x-intercept? Y is 0, right? And this is what we're going to spend a long time in this class doing, is solving things. I'm saying y is 0, so I'm going back to my equation, replacing y with 0. Solving things like this. Kier warned me that you guys didn't have much time to practice this crucial skill. Factoring? Have you ever factored before? Oh no. Oh gosh, okay, that's not good.
2 and 1.
Okay, let's try this. I'll get you started. I think it'll come back to you. Or if not, I'll teach you from scratch, whatever, we'll figure it out. Remember how you write x plus something, x minus something times x plus something, x minus something? Okay. How did anybody know how you figure out what goes right here? Anybody? You know what I'm talking about. You know. Something like that.
Oh, yeah, you hire the last number should add up to
Oh. Oh, okay, you're all right. You're all right. Let's slow that down though. You have to think of two numbers that multiply by the last one, right? Think of any numbers that multiply by to be 2. 2 and 1, right? Is there another possibility? What about -1 and -2? Is that another possibility? You got to think of all the possibilities. But one of them, that group will add to be the middle term, exactly like you guys said. So which is it, the +2 and the +1, or the -1 and the -2? The pluses. So +1 and +2. That's how you factor. Okay. We'll practice that a lot. The whole reason we're obsessed with factoring is this is gross, isn't it? It's a lot of stuff. Look at this just little piece. Isn't that easier to deal with? Whenever you factor something and it's equal to the magic number of 0, what you can do is you can figure out when these factors individually are equal to 0. That's why we're going to work about factoring so much in this class. And this answer would then be x is -1 when you move to the 1 on the other side. And same thing with this one. Move the 2 over, and x is -2. Cute, huh? We're going to spend a lot of time on that. This graph, it ain't going to be a line, is it? This graph is going to look like, well, let's try to piece it together. What did you say the y-intercept was? At 2? Okay, so it's going to cross up here at 2 on the y-axis, right? You're also saying that -1 and -2 for x's, -1 and -2, it's going to cross there as well. And if you actually did graph this with your calculator or whatever, it would look like this. Like a U thingy, and it'd go through those points just like design. So everything I'm talking about with intercepts today, please don't think it's just lines. It applies to everything. Okay? I'm now always going to try to teach you the most general thing you can know. Questions over the intercepts? Let's go on. Last topic. Let's summarize this. This is too much wordiness. Symmetry. That's the topic of this. Symmetries. 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 There's two kinds of symmetries they're going to talk about. One is called a line symmetry. What do you think that means? It's symmetric across some line. So if you took a picture of this graph and you flipped it over some line, it'd be the same thing on both sides. That's what it means. And let's summarize that in a little thing. When you flip a graph across, oh man, did it do that again? I got tech issues. When you flip a graph across just today, it started all day long. It's been glitching like this. It'll switch. No, it's just a jerk. It's just a jerk. I thought I had it. I thought I was so clever earlier. I was brainstorming. I think I know what's wrong with it. I'm gonna go and fix it. I don't know. I don't know what I'm talking about. All right, let's try this now. Okay. All right. When you flip a graph across a line and it stays the same, basically. It should be the same on both sides of the line. Okay. Look at an example of that. Here's a line, right? And I might take some kind of graph and make it look like this or something like that. Is that roughly the same thing if I took this image and I flipped it over that line? Would it kind of be the same thing? So this graph has what? Line symmetry. Most of the time, they're not going to be slanted little graphs like that. Probably something more common. Another example. Do you see a line I can flip this over and it'd be the same on both sides? The y-axis, absolutely. Right there would be my line of symmetry. That's it. Okay. You remember this? Good. Oh, you did little cutesy, touchy things? That's great. Well, man, I almost thought you said that you were gonna retain it. That'd be so good if you retained it. It was kind of confusing. Oh man, lost the whole thing. Okay, there's that. Now here's another next term. It's the only other major term. There's two subterms, but they're based on this. The other one is called not line symmetry, but point symmetry. And I just want you to copy down the exact same definition, but replace the word line with point. Yep. When you flip a graph across a point and it stays the same. Now it's working. Well, I tried to record first hour because I got first hour. And I forgot. That's my fault. Fifth hour, I tried to record it, but I kept running into all these problems. So this is my last chance. If I don't get it now, it sucks. There's a line, right? It has point symmetry. And by that, I mean, I could pick any point on this line. And if you took your graph and you flipped it over that line or that point, you'd get the same thing on this side, wouldn't you? Oh, I can take this and flip it over. I can take this and flip it over. That's what point symmetry is. It gets more complicated than that, of course. They're not all pretty little lines like that. Here's another graph. It's kind of cute. This has point symmetry. That point right there actually works. And if you don't believe me, let's do some checkpoints. Here's a spot on the graph, correct? If you take that spot and you flip it over the axis, you get a spot over on this graph. Same thing, and so on and so forth. If I pick this little point right here and I flip it over, I'd get a point right there. That's what they mean by point symmetry. Now, I'm not going to sit around on your test and say point symmetry and all that kind of stuff. There's only two main kind of symmetries that are based on these that I'm going to care about and that are going to haunt you as you go forward. And they're your last vocab terms for the day, right down there. An even function and an odd function. These are special names for a special line symmetry and a special point symmetry. And they're named even and odd for a very good reason. So I guarantee when your test comes, I will not say, go find some point symmetry. Go find some line symmetry. I'm not going to do that. I'm going to talk about these two specifically. Is this even or is this odd? Is it even or is it odd? It can be neither. It can't be both. What the hell is he talking about? This guy's drunk. Yes, I am. You don't want to know. Never drink my coffee till you're 21. I often think about that. Do you know how hard it would be to do your job? Like, oh, God. I wouldn't. Oh my gosh, that'd be terrible. Oh yeah. Okay. What's the definition of an even function, guys? When a function's graph is symmetric across the y-axis, that is a specific line symmetry. If it's the same on both sides of your graph, then I'm going to call it, well, it's got line symmetry, but I'm going to call it specifically even. That's for y-axis symmetry. There's a specific point we're going to focus on being symmetric across. It's not just some random point in the Cartesian plane, it's the origin. And if something is symmetric across the origin, our name is going to be an odd function. Those are important. Here's the most simple example I can think of. Is this even? And by that I mean what? Symmetric across the y-axis? Here's the y-axis. If I flip it across both sides, do I get the same thing? Yes. So this is even. This is an even function. What's anything to the 0 power? Does anybody know?
1.
Yeah, you learned things over the years. I'm so proud of you. Yep. Anything to the 0 power is 1. I'm going to write this in a weird way. Just trust me for a second. I'm going to write this as times x to the 0. Don't worry about y. Just trust me. Anything to the 0 power is 1. So this is 1. 1 times 3 is 3. So I didn't change it. Put this awkward thing in here, and you don't know why for this moment. This is a graph of y equals x squared. Is that symmetric across the y-axis? So what is it called? It's even again. This is even. Yeah. Here's a really weird looking thing. Is it still even? Yeah, I'm going to make an equation for it. I'm going to make something up. I'm not saying this is exactly what the equation is, but I'll say this. Something like that. Thank you. Please call me out on that a lot. It's really hard to adjust. I'm just so used to going back and forth. Even? Even? Even. Look at the exponents involved in all these examples right here. X to the what? Is 0 even? Yeah. X to the? Is that even? Every exponent in this, guess what I made them? This is why it's called an even function, because it's built out of things that are purely exponents of even. You might want to write that down. If it's even, all the exponents will be even. That's a really handy way to look at the function and just say, I can see that this is going to be even. I don't need to go get my calculator out. I don't need to go plug it all in and graph it and look at it and try to flip things. The equation itself tells me it's even. Make sense? Okay, last one. Let's do this. I wonder what I'm going to talk about last. Probably. Whoa. Now, this is the most boring linear thing I can think of. Y equals x to the first. What's the definition of an odd function? You just wrote it down. What'd you write down? Across the origin. So here's my origin, right? If I took this and flipped it over, would I get the same thing? Yes, I would. So it's odd. Someday we'll talk about this. This is y equals x to the third. Guess what? We already talked about it, but yes, if you took any point here and flipped it over, you'd have a point on the graph again, wouldn't you? And this is odd. Do you see where I'm going with this? Yeah, what do you got?
Oh, yeah, I might be missing something. I don't see how you can flip the x31 and it land where the x's are.
Well, basically, I need to take, you basically connect a line from the origin to wherever you are, right? You take that line and you flip it directly over the origin. You don't, tilt it or anything like that. Just flip it 180. And then it should land, I guess, more like right there or something like that. Another way to check if it's odd, by the way. I didn't mention this all day, but it's something to know. If you graph this and then you took your calculator and you turned it completely upside down, can you imagine what this would look like if you turned it upside down? If you completely turn it around, this part would come down here and it'd look like that. This part would go up here and look like that. Guess what? It would look the same thing. That's another way to do it. So if you have your calculator out, you can just flip it upside down. If it's the exact same graph, then it's odd. That's one thing to do. Last example. How about this bad boy? Terrible 3. Is it odd? Let's check. Here's the origin, right? Let's pick a point. This is a point. I like that. If I flip that over, guess what I get? Right there, right? If I pick the bottom and I flip it over, I get that right there, correct? So it looks to be odd. Look at all the exponents in the equation. Because they're all odd. That makes this odd. And that's how you can easily check by looking at the equation. Now, what if, last thing, what if I give you this? Are all your exponents even? So is it even? No. Are all your exponents odd? So is it odd? So guess what this one is? It is neither. Yep. I just posted it. Should be there very soon. So since it's neither, if I did go graph this thing, maybe it looks something like this. Not even, is it? And if I take any point here and flip it across this, I certainly don't get another point on it, do I? It ain't even, it ain't odd, because it's a mix of even and odd. And that concludes your lesson over symmetry and our first week of school. Okay, there you go. So you got your homework to do. Is due on Wednesday. I know you're all going to rush home and do it first thing tonight. But why don't you take a night off? Nah. Yeah.
How many questions?
The assignment's already on Reveal. Yeah. All I got to do is